This one, right?
Yes, sir. Yes, sir. This one.
Okay. See, there are a couple of ways to do this. The one that I proposed was the simplest way to go through this problem, where you assume whenever mercury is in touch with your resistive material, from this point on, you can assume the resistance to be zero. That means from here to here is a good conductor, and here to here is also an excellent conductor. So effectively, you have resistance here, two conductors, resistance here, and resistance here. That's how you get this. Okay, and because this point here in the U-shaped tube is now connected to ground, the potential here is zero with respect to, potential here is zero at this point. If you were to be very careful, right? Okay, then what you could do, is that clear? The potential here being zero, because you choose this as your reference, and the voltage that you applied here is V with respect to this point. So this point we assume to be 0 volts.
Yes, sir.
Okay. Now, if you were to be very careful about this, right? Let's assume the resistivity of mercury cannot be neglected. Okay. Then how would you address this problem? What would happen? So if you
So
have,
I was thinking to like. Okay, sir.
go ahead. Yeah.
No, so I was thinking to add two resistances, series to R2 and R4.
So here, this is, let's say this is the mercury level. So consider this to be some R1, so R2. You could consider the rest of this, right? From here to here as another resistance R2 dash. And if you want to take into account the resistivity of mercury, then you can take, similarly on the other side, you will have R4, and you will have R4 dash, and you will have resistance of whatever mercury is over there. Let's say this is R2 double dash, this is R4 double dash. Okay, now as this height changes, right? Let's say this is L1, this is L2, R2, R2 dash, and R2 double dash, all of them will change.
So
Okay. How would you find out R2 double dash or R4 double dash?
this length of
No, sorry, can you repeat that again? I could not hear you.
the resistivity of wire and mercury and
No,
the
no,
length of.
no. R2 double dash is only the resistance of the mercury. The resistance of the wire is R2 dash.
Ah, yes, sir. Like separately, we will calculate
Right. So it
the
will be the,
total area. Area will be like
so let's say this has an area of
tube area minus.
uh,
Yes, sir.
pi r square. Let's say this has an area of pi small r square. So the area is pi r square minus r square, and whatever is the length that is here. And similarly here. Okay. That would be a more accurate uh, version of this problem.
Yes, sir. Yes.
Okay, all right. So let's quickly now review things that we covered last class. Yeah. What did we talk about last class?
So pressure,
What is pressure? What is pressure?
force applied per unit area.
Okay. Hmm. Thank you. The SI units are Newton per meter square, which is also called Pascal. Okay. And then, so we were interested in measuring pressure. How do we measure pressure? So one we just saw. You can use this setup. What are the other methods that we saw or that we discussed?
Force-based pressure sensor.
Right. And how do we do that? So we use some elastic element. So when you apply a pressure over a particular area, then that results in a force that acts on this elastic element, which leads to a deformation, some deformation, which is then measured to get pressure. Okay. What are the different elastic uh, pressure sensors that we discussed?
Diaphragm is
Sorry,
the diaphragm is
sorry, I can't hear you properly.
hello.
Yes,
It's the first one I know is diaphragm based.
right. The most common one is where you have a diaphragm. It's clamped. So if you apply pressure, then this diaphragm undergoes a deformation. And by measuring this deformation, we can now measure uh, pressure. And how do we measure deformation of the diaphragm?
Via two strains wherein the radial strain and the tangential
We
strain.
have a circular diaphragm, there is a radial strain, and there is also a tangential strain. There are different ways to do this. You can have a strain gauge here for measuring the radial strain, and a strain gauge here for measuring the tangential strain. But you also have strain gauges that are specifically made for radial strain, and strain gauges made for tangential strain. Okay. So measuring the strain is one way of getting to pressure. What is another way that we discussed?
So Ballot-based.
What based?
Ballot, BALLOW.
Ah, yeah, sorry. Yeah. This is another method where bellow is a bag, specific design, so that when you blow in air at a particular pressure, this will undergo an expansion, and we can measure the change in length of the bellow to measure pressure. Another type using the diaphragm concept. The capacitive sensors, where the deformation of the diaphragm now leads to a change in capacitance. So we are not really measuring the strain on the diaphragm, but we are the diaphragm is arranged in such a way that the diaphragm forms a plate of a parallel plate capacitor, and when the diaphragm deforms, that changes the distance between the diaphragm and the fixed plate. That leads to a change in capacitance, and that is another way of measuring pressure. And then, what did we talk about after this?
Piezoelectric change in current.
Piezoresistive.
What is this?
Piezoelectric.
The formation of charge due to change in pressure, change in stress.
Generation of charge due to stress. Um, and then we talked about, let's say this is a piezoelectric material, and let's say there are stresses acting in different directions, x, y, and z. Let's say we are only focusing on tensile or compressive stress. Then the polarization that is induced in the different axes, dx, dy, dz, is related to the three stresses through this matrix, which is called the piezoelectric coefficient. Well, each element is called a piezoelectric coefficient. And we know what do the diagonal elements tell us?
The axial strain, like polarization along x-axis
Right, yeah.
due to stress in x.
Right. Polarization along a particular axis, along x, y, or z axis, due to a stress acting along the corresponding axis. The diagonal elements, on the other hand, tell you the transverse effects. For example, this would be polarization along x due to stress along the y direction. This is polarization along the z because of a stress acting along the x axis. Okay. And in general, if you have a piezoelectric crystal, you would use the crystal in a direction where your piezoelectric coefficient is quite large. Right? So that for a particular given amount of stress, you get maximum polarization. Okay. So let's now continue.
Excuse me, sir.
Yes.
Sir, in the previous class, when you discussed regarding the course of the polarization that will happen when we compress the piezoelectric material
Yes.
or stretch that, so can that course be interchanged? I mean, when we compress the force, there is positive above and negative down. So can it like happen otherwise as well?
Yes. So yeah, let's say this particular crystal is only sensitive along the x-axis. That means the matrix is like this. Some d. So we only have to worry about uh, polarization along the x-axis is some dxx times or du sigma xx. Right. So here, this tells you that if you have the crystal and if you apply a force like this, let's say a positive charge appears here, a negative charge appears here. Now, if you reverse the direction, so that now your sigma xx is negative, instead of being compressive, it's tensile, then this also gets reversed. So then the direction of polarization also gets reversed. So it will act in both directions.
Uh,
Okay.
how do we decide that which polarization is will happen upon compression or
That depends on the crystal though. See, what is going on is the crystal that you have uh, already has uh, dipoles at the molecular level. Okay? That means there is charge separation within the molecule.
Mhm.
Say like this. Now, if you apply a stress from outside, the molecules change shape. Okay. Something like this. In this particular case, the molecules are arranged in such a way that when you apply a horizontal force, uh, so here you're applying a force along, let's say, the x-axis, but your output appears along the y-axis. So the coefficient that we are dealing with here is this. Okay. So here the molecules are arranged in such a way that if you apply a compressive force, positive appears on the top, negative appears at the bottom. Whereas if you apply a tensile strength, the opposite happens. Okay, so that which side becomes positive and negative depending on the nature of the force that you're applying depends on the crystal. Okay. Again, I think this we discussed last time. So we call something a longitudinal effect if the direction in which the stress is applied and the direction of polarization is the same. So in this case, you are relying on the diagonal elements of the matrix. If it's a transverse effect, then the direction in which you apply the force is orthogonal to the direction in which the polarization appears. Okay, this is a transverse effect. Here, this is a transverse effect. Okay. All right. Now let's look at. Let's take the piezoelectric crystal, because there is now charge separation, so there is an electric field that is set up inside. And now, if you take the piezoelectric crystal, these are the piezoelectric crystals are usually insulators or dielectrics. If you deposit a metal film on either side and you take a lead out, right? And now, if you apply force, right? Let's say we are discussing the transverse effect now. This crystal has a transverse electric field that is generated depending on the force that is applied. Right. Now, if you deposit a layer of metal on both sides, take the leads out, and then if you apply a force and you connect a voltmeter here, right, the voltmeter will read some voltage. Okay, and the voltage that we read uh, will depend on two things. Okay. It will depend on the amount of charge separation that has happened, or the amount of polarization that has happened in the crystal, and it will also depend on the geometry of the crystal itself. Okay. Now, what we've done here is by depositing two metal films, right? We now have a conductive layer and a conductive layer separated by a dielectric or an insulator. What is this? When two metals are separated by a dielectric, what does that particular arrangement result in? What does this arrangement behave like?
Capacitor. Capacitor.
Right? This will behave like a capacitor. So it turns out that the voltage that you will read between these two terminals will depend on the amount of polarization that has happened and the capacitance C of this particular arrangement. For now, let's assume that the piezoelectric crystal is like this. It has an area of cross section of D. It's a cuboidal shaped crystal. You deposited a metal layer of metal here and a layer of metal in the bottom, and then we've taken the leads out, and we're applying the forces in this direction. And let's assume the dielectric constant of the piezoelectric crystal itself is epsilon. Okay? And the thickness of the crystal is L. What will be the capacitance of this particular sensor now? Is the two metal plates and the dielectric in between.
Epsilon A by L.
Right? So that will be the capacitance. See, this is L. Now, let's say there is the piezoelectric coefficient of this crystal is D. Now, if there is a force F acting on the crystal, what will be the charge that will be produced?
E into S.
Right. That's given by D. This is amount of Coulomb generated per unit of force. So this will be E to F. Right? Now, if you substitute for, and we know capacitance is nothing but charge per voltage. If you substitute this here, then you will get a relationship between force and voltage. Okay. The force that is acting in the horizontal direction will result in a voltage V, or we can write it the other way around. The voltage that will be read by the voltmeter will be 1 by epsilon L by A dF. This is the voltage that we will read. And now this gives us a sensor that can be used for measuring force or pressure in this case. Okay. Now let's say the area of this is some A dash. Okay. And the force that is applied on either side, let's say it acts uniformly on this area. What is the pressure acting on the two sides? The force is F. The pressure that's acting is basically F by A dash. Okay. So we can now compute the pressure from the force by simply dividing this by A dash. Okay. So that's how you get a pressure sensor out of this. Now let's just do a simple problem. Let's say we have a piezoelectric crystal shown like this, and here let's say this crystal is, we're looking at the longitudinal effect. That means the direction in which you're applying the force and the direction in which axis along which the polarization happens is the same. Given the different values for the dimensions of the crystal, the dielectric constant, and the piezoelectric coefficient, tell me what will be the charge that is generated by a force of 3 Newton that is acting on the top and bottom surfaces. Tell me what will be the capacitance of the sensor and the voltage that we will read between these two terminals. Maybe let's start with the capacitance. What is the capacitance of this particular arrangement? You can compute and tell me what the capacitance is.
Two into 10 to the minus 12.
Okay, 2 into 10 power minus 12 then. Is that right? 2 picofarad. Yeah, is it 2 or is it 4? It's 2, is it?
4, sir. 4.
It's 2, sir.
No, it has to be 4 because it's epsilon
Four.
A by
Four.
T. T is
Yes.
half, so it has to be 4. Okay, what about the charge that is generated?
5.4 picocoulomb.
5.4, is it? Picocoulomb. And so what will be the voltage that we read? What is the voltage?
1.35.
Okay. All right. So with this arrangement, for small amount of force, we are able to read a reasonable amount of voltage. Okay, even though the capacitance is very low, the charge is also very low, so we are able to read reasonable voltage. Okay. The point to note here is the capacitance associated with these are generally quite small. See, now the question is, okay, we have the piezoelectric crystal. The piezoelectric crystal, when we apply a force, it leads to a polarization within the crystal, and by depositing metal films on on two sides, and then we can measure the voltage is generated. Now the question is, how do we model this particular sensor? Okay. One way to think about this sensor is because there is a capacitor and it generates a voltage when we apply a force. We could say, well, the electrical model for the piezoelectric crystal is like this. It generates a voltage. And C is the capacitance of your sensor. I'll call it Vs. Note that this Vs is a function of the force that is applied. The capacitance is constant, but Vs itself is a function of the force. We will assume that when we apply the force, of course, the crystal will undergo slight deformation. That the deformation is small enough that it does not lead to a big change in your the capacitance of the sensor itself. So we'll assume that the capacitance itself is approximately constant. But the voltage that is generated will depend on the force, which we saw earlier here. Right? The voltage is a function of the force. So this could be a model for our sensor. But it turns out that this is not a good model, because if you take, let's say you take the piezoelectric crystal. Usually it's drawn like this. You apply a force, and then you read the voltage. Let's assume that we're using an ideal voltmeter. So let's say the voltage, and it has a capacitance C. Let's say the voltage we read is V. Now, say you connect another capacitor in parallel here with some capacitance C1. Okay. Now you apply the same force F. If the piezoelectric crystal was a voltage generator, right? If this was in fact a good model for our, the correct model for our sensor, then what would be the voltage that you read now? So this is only sensor. Now we have sensor plus capacitance. If this was the true model of the sensor, then what would be the equivalent circuit for this? It will be voltage source Vs in parallel with Cs and then parallel with C1. So what would be the voltage that we would read now?
Vs.
It will be Vs. So here it's Vs. Right? We should read Vs. But it turns out we don't read Vs. What we read turns out to be something
Less
lower
than
than Vs. Okay, and in fact it turns out that what you read is, if this is Vs, the voltage read is Vs in the first case, right? What is the charge on the sensor, given that Cs is the capacitance of the sensor?
Q to CV, C
C
into
by
Vs, C1 into Vs, CS into Vs, sorry.
It turns out,
CS plus C1, won't it be CS plus C1?
No, for
the first scenario
second,
here, only sensor. Okay, now,
C.
okay, so it turns out now in this particular arrangement, the voltage that you read V dash will in fact be uh, Qs by Cs plus C1. Okay. So what is actually being generated by your crystal, piezoelectric crystal, is not a fixed voltage, but a charge that is a function of your force. So if you apply a particular amount of force, what is actually generated is a charge. Uh, we measure a voltage because we have instruments for measuring voltage, and because we formed a capacitor here, the charge now leads to a voltage across the capacitor, which is what we are measuring. But now, if there are other capacitances in parallel with your piezoelectric crystal, it turns out that the voltage that you read will be different. Okay, so a better model for your piezoelectric crystal is, of course, the capacitance, because there is a capacitive element there. In parallel with, because it's generating a charge, this should be some charge generator. But the only two sources that uh, we've discussed so far are that have been found to be quite useful for analyzing circuits is a voltage source and a current source. What is an ideal voltage source? Just a quick review.
In series with a resistance, voltage in series with resistance.
No. I'm asking you, what is an ideal voltage source? I mean, I can connect any voltage. I mean, I can connect a battery in series with the resistance, right? Does that mean that the battery is an ideal voltage source?
How much may be the current, but the voltage across the end should
Right.
be V.
So no matter what you connect here, RL, let's say this is RL, and this is the voltage across RL, VL, it will always be the same. So let's say we shall be V or VS, the source voltage. What about a current source?
The current should be same no
Exactly
matter
the
what the
same. So if I
voltage is.
connect a resistance RL and I look at the current that is flowing, IL, and I plot IL versus RL, it will be the same, IS. So no matter, for a voltage source, no matter what current you draw from the voltage source, the voltage across its terminals will be the same. Similarly, for a current source, no matter how much is the voltage across the current source, the current coming out of the current source will be the same. Okay, so these are the only two sources that we've used before, and because we don't have a charge source, we can model this as a current source in parallel with the capacitance Cs, except now the current Is that is that results from your force will have a slightly more complicated form. For example, the current that, so when you apply a force on the piezoelectric crystal, we can assume that there is a current that is generated by your piezoelectric crystal such that uh, the charge that is deposited on this capacitor will be Q. Okay. Your piezoelectric crystal. Initially, let's say this is time, and this is the force that is acting on the sensor, and this is time, and this is the charge on your sensor. There was zero force initially, and then at some time point you apply a step force of magnitude F, I don't know, F1. What will be the corresponding charge deposited on your generated in your crystal?
EF1.
Yeah, it will be some
Aryan.
Q1. Q1 will be V into F1. Right? Now, if we were to model this charge generation process through this circuit, right? What should be I now as a function of time?
Ramp function.
think about it again. Here, when you applied the force, an instantaneous charge Q1 appeared across the capacitor. Right? So, in that case, what should have been the current that was generated for you to get an instantaneous appearance of charge across the capacitor? Here, the clue is here. If Q is integral of current over time, what is current?
Derivative of charge.
The impulse.
Yes, exactly. So, the current that would have been generated by your would be an impulse function whose strength is basically Q1. Okay, because now if you integrate this I of t, you will exactly get this. Okay, so one way to think about the piezoelectric crystal is a current source in parallel with a capacitor, but the current that is generated by your current source will not be directly proportional to force, but it will be directly proportional to, because charge is directly proportional to force, current must be directly proportional to the rate of change of force. Is it clear?
Yes, sir.
That's an equivalent model for your electrical equivalent circuit for your piezoelectric crystal. Okay, now let's go back to um, the
Excuse me, sir.
yes.
If I apply my capacitor in series with my voltage source, uh, would that make any difference with that?
Sorry, what do you mean?
If I apply you, here we have a current source in parallel with the capacitor.
Right.
Now, if I have a situation where I have a voltage source which is connected in series with a capacitor, uh, will that be somehow equivalent circuit of my piezoelectric sensor? V minus.
Yeah, okay. I understand what you say. Is this an equivalent circuit? No. So here, if I connect a voltmeter here, right? Let's say I apply a force. What would be the voltage that I would read? It will be V of F. What is the charge that is deposited on your plates? Nothing, no? Because so if I read, if the voltage, if I apply a force F, it generates a voltage Vs. What I will read here will be Vs. That means the voltage across this is zero. That means there is no charge across the capacitor, but there is charge across the capacitor.
I mean, won't this capacitor draw some of the charge
No,
in
it
that?
won't. It won't, right? So, for example, let's say it does have some charge deposited. Then what would be the voltage? And that means there is a
Equivalent.
voltage, some voltage v dash across the capacitor. Then what is the voltage that you will read with your voltmeter?
Equivalent.
Not equivalent. It will be Vs minus V dash, which is not correct. That's not what you will read. No, I don't think this is an equivalent circuit. This is not equivalent to this.
Yes.
Yeah, let me hold on. Let me think. No, actually, you're right. Hold on. Let me think about this a little bit more. Here, actually, I think my analysis was wrong. If you have something like this, see, if you apply a step voltage, a step force, right, generates a step charge, that means the current generated here would be an impulse. Now the question is, what would be the equivalent? I mean, the question is this equivalent to this? The question is, if current has an impulse function like this, what will be the voltage? If you have a voltage and you connect an ideal voltmeter here, no, it won't be, right? Here, if the voltage is like this, then the voltage that you'll read from your voltmeter also will be like this. But this is not what you read. What you read as a voltage when you apply the force is like this. No, so it won't be, no. So this is not equivalent to this.
Sir, so what has changed between the case when the capacitance was in parallel to this case? Sir?
Sorry,
And if you
capacitance is
see,
in parallel with the voltage source.
yes,
We saw
that
that,
time
right?
you are saying
We saw
it
that, right?
should.
Here, it's a
Yes, sir.
problem.
That time you are saying the capacitance will draw some, like, gain some charge and gain some voltage. But when it is in series, you're saying it won't be.
It won't, right? See here, if the capacitor has any charge, right, there is a voltage across it. Let me call it VC, because VC is, okay, let's say Vs is proportional to the force that you apply. Now, if I connect a voltmeter across this, I'll read a voltage. The voltage that I read will be Vs minus Vc.
Yes, sir. Yes, sir. Now I get it. Yes.
Vs minus Vc or plus Vc, depending on the sign of the two voltages. So the only way you will, so if you apply a force F on the sensor, you will read Vs. That means there is no charge on the capacitor, which is not correct. Because we know there is charge separation, and in fact there will be a charge on this capacitor. Okay. Sorry, somebody was saying something.
My question is that even if we apply a step input as a at the in as an input as a VS, what
Sorry,
we would be getting,
what is the input? The force, is it?
I mean VS, yeah, the for in terms of force as a function of force.
Okay.
So in this VS in series with the capacitance here in the circuit, so what we would be getting at the output will it won't change. I mean there that would be again a step function
All
rather
right.
than
Okay. What is the role of the capacitance here then?
it will draw some charge,
It won't.
but
Won't. Because the moment it draws some charge, there is a voltage drop across it, which will be reflected in the voltmeter reading. Okay. Yeah. So this does not work. Now here, what would happen if I take my piezoelectric crystal and let's say there is a capacitance that is connected in parallel. This was your what is the voltage that I will read here. Let's assume the voltage Vs here is proportional to the force. What voltage do we read here now?
Vs into 1 upon SC1 is on 1 upon SC1 plus 1 upon C1.
Sorry, can you be louder? I can't hear you.
A voltage division rule.
Sure, but that's not what we would read though. What we would read would be a voltage that is, let's say, if there is a charge Q across both these capacitors. Just for example, right here, if it is in this case, the voltage we would read would be different. Now, would you get the same voltage here? Yes. That's not what you would get here though. Two capacitances. The voltage that you end up reading would be total charge that is drawn. Two capacitances are in series. QS. Yeah, let me think about this. See, I would say that this is not an equivalent circuit just because of this reason. But let me also try and see what this gives us. If you connect a parallel capacitor, what you should read should be CS by CS plus C1 into Vs. The voltage would drop because the total capacitance went up. But if this was your equivalent circuit, this was another equivalent circuit uh, for the piezoelectric crystal, and you connect a capacitor like this. I need to think about what would happen if you connect two capacitors in series like this. If you assume that there is no initial charge in them, then they would have a particular charge distribution between them so that you get some Vs and V1, and the sum of those two will be equal to your, sorry, not Vs, I'm calling this Vs, V and V1. The question is, what would those two be? Impulse current would flow. So both of them would have to have the same charge. If they have the same charge, Q, Q, So this is the voltage you read. How is that related to? Yes. So this is the voltage you will read, which is not the same as this. So this cannot be the equivalent circuit. Is your idea? Or no?
Yes, sir. If the current is same on both capacitors,
Yes.
so can I get the current on one capacitor by like total capacitance? I have equivalent capacitance Vs by total capacitance by 2.
No, the current that is flowing through the capacitor will depend on the rate of change of voltage. The relationship between capacitance and voltage gives you charge.
Mm-hmm.
So see, this is what will happen. The moment you connect Vs, let's say there is no charge on these two capacitors. There is no charge. Initially, there is no resistance. The moment you, let's say there is a switch here, right? See, there is a switch here. Initially, there is no charge. The moment you connect this, right, an impulse, if you monitor the current I and you plot it, let's say we close the switch at time t equals 0, the current will be 0, and then there will be an impulse current, and it will be 0 again. Because the same current is flowing through both of them for a very short period of time, the same charge would get deposited on both of them. Okay? If the same amount of charge is deposited on both of them, then their voltages would be simply V would be Q by Cs, and the voltage here would be. Now the question is, compared to the previous case, where you had Cs, the voltage here was Vs, what would be V1? V1, it turns out, would be C1 by But if you take the piezoelectric crystal and you connect additional capacitances in parallel to the crystal, the voltage that you will find will be this, not C, just C.
Yes,
Okay.
and we consider C1 is very small.
Sorry,
Like we consider that C1 is very small. That
where did we consider Cn to be small?
C1, sir. C1 to be small, then we will get V dash to be Vs.
Yes. So if there is no capacitance, then then V dash will be Vs. That's the first scenario.
Yes, sir. Yes.
Okay. Okay. Let's continue. All right. So now we saw earlier. That's it. We'll now use the equivalence. This is our crystal. Generate some I of t, and this gives us some voltage, right? Now, because this crystal itself generates some voltage, uh, and usually the pressures that we are dealing with, the effective force that is acting on the crystal itself will be very small. The area of the crystal, so the charge or the voltage that is generated will in general be quite small. It won't be like the case that we discussed here, because the force here that we applied is relatively large for the kind of application that a piezoelectric crystal would be used for. Okay? So the voltage that you will get would be fairly small. So what would we do? So we take this voltage, right, and then connect it to a voltage amplifier, which let's say has a gain of G to generate an output of GB. Okay, but it turns out there is a problem, and we saw this earlier, right? Now, if you take the piezoelectric crystal, if you have wires coming out like this, right? These are two metallic conductors separated by air in between them. That means these have some stray capacitances, which are usually quite small as well. Right? Now, because the capacitance of the piezoelectric crystal itself is quite small, now you have two parallel capacitances. Because their magnitudes are now comparable, the voltage that you get across your piezoelectric crystal will change if you change the length of this wire, the distance between the wire, or if you move the wire, so that their geometric configuration is now different. So the voltage itself that you read across your piezoelectric crystal is very sensitive to stray capacitance. Okay, let's say you have your crystal, and then you've got some wires running to an amplifier, and then you've connected this to a voltmeter. Now, if you slightly move the sensor without changing, or if you slightly move the amplifier here, so that the wires are now like this, you find, let's say the initial voltage was V, now you find that V dash, you will find another voltage V dash which is not equal to V, even though the force acting on the sensor itself is the same. And the reason your output voltage changes so much is because by moving the amplifier and the wire, you change the amount of stray capacitance. So it turns out that your piezoelectric crystals are very sensitive to this, so you cannot rely on the voltage signal. Okay. And that leads to that led to the use of what are called charge amplifiers, where what you're going to do is not rely on the voltage signal across the two terminals of your piezoelectric crystal, but rely directly on Q, which is proportional to the force that's applied. Okay, Q is fixed. What changes is your voltage depending on the amount of stray capacitance there is. Okay? And a simple charge amplifier is given here. Okay? The idea is this circuit is fairly simple. Okay? So you take your op-amp, you ground the positive terminal, you connect your piezoelectric crystal to your to the negative terminal, and there is a feedback capacitance CF. Now, because there is a feedback path, negative feedback path, let's assume that again we'll assume this is an ideal op-amp for now. Okay. Now, if there is a finite output at your the output of your amplifier, since the gain is infinity, the voltage difference between these 2 points should be 0. Okay. That means you're forcing, by connecting your piezoelectric crystal to a circuit like this, you're forcing this point to be at the same potential as this, which is at virtual ground. Okay, so whatever, and the current, because you're forcing this point to be at ground, what happens is there is no charging of the capacitance of your piezoelectric crystal anymore. So this is connected to ground. If you generally apply a force here, this plate gets charged. The plates of your piezoelectric crystals get charged, and that's why you read a voltage here. But now, by connecting this in this particular configuration, because we force this point to be at virtual ground, there is no charging of the capacitance here. Your piezoelectric crystal will, the current that is flowing out or flowing in, depending on the direction of the force and the polarization, is now forced to charge this capacitance. Okay, which then leads to some V out here. Now the question is, how did this solve the stray capacitance problem? Okay. It solved this stray capacitance problem is because now let's say you have your piezoelectric crystal, and then you had a long wire. Ground. Taken this. Whatever stray capacitance there was between, because you force these 2 points to be at the same potential because of the use of this high gain amplifier with negative feedback. None of these capacitors cannot assume any charge now. The current that is coming out of your piezoelectric crystal is forced to charge this capacitance only, thus removing the effect of any capacitance here. Is it clear?
Yes, sir.
And so the output that you get will be given by this. The current that is generated is now forced to flow only through the feedback capacitance. Okay. So the output that you will have, because it's connected to the negative terminal, there will be a minus sign. The output is now inversely proportional to your CF. So by choosing an appropriate CF, you can now amplify, and this is nothing but your charge that was generated. Effectively have Q by F as your output. And notice that CF is what we choose. So we have complete control over the voltage that is generated because of the charge generated in the capacitor, in the piezoelectric crystal.
Hello, sir.
Yes.
Can you explain this long wire part again a little bit more?
So what do you not understand?
I mean, why has the ground changed? Like, I was trying to understand that.
Sorry, what has changed? Ground has not changed, no?
Then how these came, like, these wires?
Sorry, okay. Are you asking if you have two long wires like this, why there is a stray capacitance between them?
Yes, sir.
See, what is a capacitor?
Capacitance. It is a separation of charge and which has a material in between.
No, capacitor. So a capacitor is any two pieces of conductive material that are separated by a distance. Okay. So now, if I deposit a charge Q here, right, there is an electric field that is set up from this. Let's say I deposit a charge plus Q. Okay. Now I have metal here. One. Fine. Let's say I deposit a charge of plus Q here, minus Q here. There is an electric field that is set up. Now, if you simply connect a voltmeter across this, you will see a voltage. Okay, and the voltage that you read here will be different if these two metallic conductors were like this, or sorry, this is minus. V1, this is V2. The two metallic conductors are the same. But what is changed is is the separation between them. If you change the separation, that leads to a change in your voltage. Or if you change the amount of charge that is deposited on these two, that also leads to a change in the voltage. Okay?
Yes, sir.
So anytime you have two metallic conductors that are separated by some dielectric material in between them, that means they can act as a capacitor. Okay, so the circuits that you build in your lab also, so you've got connecting wires going from one pin to another on a breadboard and stuff like that. Between any two uh, uh, wires, there is a stray capacitance. Don't observe it in most of the circuits that we're dealing with because the stray capacitance is low and the frequency of the signals that we're dealing with are relatively low. That means the impedance between these two wires because of the stray capacitance is very high. Remember, the impedance because of due to a capacitor increases with decrease in omega because it's 1 by j omega c. That's why we can often ignore them because our frequencies are low. So there is effectively no connection, electrical connection between the different wires that you have. Okay, but if you start working with higher and higher frequencies, then you really have to take into account the stray capacitances between your conductors. That's why the design of, let's say, electrical circuits on a PCB for high frequencies signals is not trivial because see, you've got various wires that are going around, there are components here. Because these are conducting wires separated by an insulator in between, there is a capacitance in between them. And if you start working with very high frequency signals in gigahertz range, then you cannot ignore these capacitances anymore because they will affect the performance of your circuit. Okay, so now coming back to here, now the question is here, why is it causing a problem here? Right? It's causing a problem even though the capacitance is very small, is because the sensor that is generating this voltage signal also has a very small capacitance. Okay, and what this sensor is generating is charge. Okay, so now if you have wires that are leading out of this sensor before they connect to some signal conditioning circuit, if they are let's say long, then there is some stray capacitance associated with them, and if this capacitance is comparable to the capacitance of your sensor, then this charge that is generated will get distributed among these capacitors in such a way that the voltage that you read here will be different from the voltage that you read here. Let's say you take an ideal voltmeter, you have a long piece of wire. Let's say you measure the voltage here from your piezoelectric crystal. You'll see read some voltage V1. Now if you move it right here and measure it here, sorry, I'm wrong. Okay. Now let's say you change the wires or you cut the wires short so that the wire is only so long. Now if you measure the voltage across these two terminals, it will be different because now the capacitance between your that is in parallel with your sensor is different. Or if you change the positioning of these wires, that will also change things. Now because voltage is very sensitive, is very voltage equals Q by C. This is fixed. The charge generated by your piezoelectric crystal for a given amount of force is fixed. So if C changes, that will lead to large changes in your voltage. That's why you cannot rely on the voltage, because C not only depends on the capacitance of your sensor, it also depends on the stray capacitance. See, to give you an example, the piezoelectric crystal, let's say there is a long wire. Let's say this long wire has a capacitance of 1 femtofarad, very small. Let's say the capacitance of your sensor itself was, say, 1 picofarad. Okay. What is the effective capacitance now of the circuit here? The effective capacitance between these 2 points is 1 picofarad, but what will be here?
2 picofarads.
Sorry?
So 2 picofarads.
No, I said femtofarad, sorry, 10 power minus 15 farads. This is 10
Sure.
power minus 12 farad. This is 10 power minus 15 farad. This would be 1.001 picofarad. Not that much. So that's not a problem. But what if this was in fact, let's say, even 0.1 picofarad? Then there is a 10% change in your capacitance. But in fact, if this was 1 picofarad, then you've halved or you've doubled your capacitance. That means the voltage that you will see across your terminals here will now be halved. And if I move this around, this voltage can change drastically. That is the problem. Is it clear?
Sir, hello.
Yeah.
Yeah, so sir, what should we like? Is this like done in on the purpose, or we are trying to reduce it
What is done on purpose?
using long wires?
No. Ideally, you don't want to have long wires, and ideally, you don't want that your see. It's like this. You have your sensor that's sitting somewhere. You have to take some electrical connections out to connect to your amplifier. This is your sensor. I don't want a situation. Let's say there is a force F acting on the sensor. If the output that I read, D out, changes depending on whether I place the amplifier here. If I place the amplifier here, I don't want that situation, no? Because then it's really problematic that I
Yes, sir.
cannot that I move the amplifier and I get a different output. That means I cannot move this around, I cannot take it to another place and make the measurements. That means you want to get rid of the effect because of the stray capacitances. And the solution for that is your charge amplifier, where your piezoelectric crystal is connected to this negative, your op amp in a negative feedback mode, such that the effect of the stray capacitance is taken out, because by making this connection, you are forcing the effect of the capacitance of the sensor and the stray capacitances to be zero, because you're not charging any of these capacitors. You're forcing the charge that is generated in your piezoelectric crystal to charge this capacitance CF, which you have complete control over. So if we use the charge amplifier, the movement of this amplifier itself will not affect the output that we get. But if we use the voltage amplifier, then the output that you read will be different in each of these cases, or can be different if the stray capacitance is changed by a large amount. Okay.
Excuse me, sir.
Yeah.
In the figure there of the charge amplifier, there would the CS capacitor will be charged by some amount, and by the virtual ground concept, the voltage at the negative terminal will come down to zero.
Yes.
So, and then again, further that CF will. So, my question is to you is, if ultimately at negative terminal my V is getting zero, how is going to charge the CF? Because whatever that we have having is
No,
zero.
no, here. There is a current that is being generated by your crystal, right?
Yeah.
If no current can flow through this, where will that current flow? The only path for the current is to flow through this and then flow into the op amp. That is how you're forcing it to charge your feedback capacitance. Is it clear? See, the current cannot flow through this, because if the current flows through this places a charge. That means there will be a voltage across this. So you're forcing the voltage across this to be 0, so the current has to flow through your feedback capacitance.
In the process of not charging my input capacitance,
Yes.
we are so if we are not using the seed, is my CS acting as a capacitance?
Sorry, I cannot hear you. Your voice keeps breaking up.
Hello,
Yes.
hello.
Yeah.
Is CS here by any chance acting as a stray capacitance?
No, it's not. It is the capacitance of your sensor, and there are lots of other there might be other stray capacitances here as well.
So how are we basically forcing the CS to not charge? I mean, if it is not getting charged, so how are we basically forcing this IT to flow from CF, not the CS itself?
See, if the voltage across CS is 0, can there be a current that is flowing through it? Or what will
No.
happen if there is a current, if a current flows through the capacitor?
If if I goes through CS, there will be some charge across my capacitor, and that voltage that charged will be go down to zero
It won't.
at
Why?
the input.
No, sorry, hold on. Why will that charge go down to 0? What? So if you say the charge goes down to 0, that means there is a current that is flowing through. Where is that current flowing through? You know what I mean? Here. See, it's the same as here. R1, this is R2, this is some I. What will give an output now? R1, R2. What will be my output?
Uh,
Here, there is a finite voltage here. If since the gain of the op amp is very high, these two have to be almost at the same potential. That means I can approximately assume this to be at ground. If both the ends of my resistor are at ground, there is no current flowing through this. So the current that is generated by my current source has to flow through this and then find a return path back here.
V naught in this condition would be I into R1, then minus I.
Now, why is there no current flowing through my resistor? R2, sorry. Why is there is no current flowing through the resistor R2? Because these two terminals are almost at the same potential. So, see, if you were to, in reality, there is a very small current that is flowing through R2, which is what gives rise to a tiny voltage difference here, which is what gets amplified and appears as V0. If you were to do a more realistic analysis of the circuit, of course, there is a small current that flows through R2. The higher the gain of the op amp, the lower the current that will flow through R2, because these two terminals will be at more and more closer in terms of their potential. So whatever current is generated now, most of it is now forced to flow through R2 and through the rest of the circuit in the op amp and then return back. Same idea applies here. If I force these two terminals to be of a capacitor to be at the same potential, I can do that by shorting these two. What will be the current that flows through the capacitor now?
There will be no current flowing through the capacitor that
Yes.
will be short circuited.
Exactly.
The whole, yeah.
Except now, think of this circuit The op amp, because of the nature of its input-output relationship, you virtually short these two. That means the current is now forced to flow through some other path and then come back. That some other path is your op amp and your capacitor. While it's taking this path, it ends up charging this capacitance, which is what leads to us observing a voltage V0.
Yeah, yes, sir.
Okay, all right.
Thank
I'll quickly go through the last slide. There is one important thing that we have to notice or keep in mind about a piezoelectric crystal. Turns out that, let's say this is your force that is applied, okay, with respect to time. This is F. This is time. If you monitor the charge now across this capacity, across the piezoelectric crystal, right? There is no charge till here. So far in our discussion, okay, based on our discussion so far, what would you say would be the charge on the capacitor now? Let's say a positive force produces so this force produces some charge Q. What will be the output graph for the charge, plot of the charge versus time?
Same as force.
Yeah. So based on our discussion so far, this is what it would look like. We would say this is what it would look like. It turns out it does not look like this. What it looks like is this, more or less like this. And when you go down, okay. So what ends up happening is when you have your piezoelectric crystal and you're applying the force F. Initially, let's say there is no polarization. The moment you apply a force, right, a transient charge appears across these two, and over time, this charge starts to disappear. Sorry, somebody's mic is on. Can you please switch off or mute your mic, please? A transient charge initially appears after you apply the force, and if you keep applying the same force, it turns out over time the charges will now start to disappear. Sorry. Over time, these charges will now start to disappear, and then eventually it will be gone. This is what will happen with all piezoelectric crystals. So one issue with the piezoelectric crystal is that we cannot use it for measuring a constant force. Okay. It means the input-output relationship, where the input is force, the output is charge. Your piezoelectric crystal behaves like a capacitor. If you remember for example, simple example of high-pass filter that we saw, you apply voltage V in, and you observe the output V out. If you apply V in like this, what will be the output? It will look like this. Okay. So your piezoelectric crystal behaves the same way. And if you were to plot the frequency response of your piezoelectric crystal, that means you take your crystal, you're measuring the charge that is appearing, and you're applying a force F, but the force that you're applying is sinusoidal. So you're applying force on the sensor of different frequencies, and you're observing the corresponding output charge that appears. The charge that appears will also be sinusoidal. Now, if you take the ratio of the amplitude and the phases of these two, and you plot the let's say you take the magnitudes of these two, and you take their ratio. So you plot Q by F. as a function of omega, you find that it looks something like this. It has zero gain. Zero. So if you apply a DC input, the output of your piezoelectric crystal will be zero. So you cannot use it for measuring constant forces. But it's good for measuring stuff that are time varying. Okay, and you'll also find that if you keep increasing the frequency, there'll be a frequency where the charge generated is quite high. This is the resonant frequency of the crystal, and this is usually in the megahertz range. It means the mechanical force that you're applying is quite fast. It's in the megahertz range. That's why these are excellent sensors for picking up ultrasound waves. Okay. When the frequency is close to something in this range. And before we conclude, right? Another interesting thing about your piezoelectric crystal is we saw that if you apply a force, then a voltage appears here. This is your sensor. You apply a force, you get a charge or voltage. Turns out that you can reverse the direction of these arrows. Turns out now if you apply a voltage that deposits some charge on your piezoelectric crystal, you can actually generate force out. That means if you take the crystal and you apply some voltage across it, it will change shape. Okay, and that means we can, by applying, now if you apply a sinusoidal voltage, it will produce a sinusoidal force or sinusoidal deformation. And if you apply your input in the megahertz range, it will produce mechanical output in the megahertz range. That means you can use it for generating sound, or many times they are used for, or these are also used for generating as generators of ultrasound. So you can use a piezoelectric crystal to both generate ultrasound and also record it. This is what is used for any ultrasound scanner that is used for various applications.